Morning, everyone. I'm Tony Zhang. I'm currently an engineer at Databricks. This talk is about Basilisk, a framework we built during my PhD at the University of Michigan. Basilisk introduces the new concept of provenance invariants to greatly automate the task of formally verifying distributed protocols. This is joint work with Keshav Singh, Chajed, Manos Kapritsos, and Bryan Parno. So as we all know, distributed systems are notoriously difficult to design correctly. This is due to their scale and their need to handle all kinds of non-determinism, such as server failures and asynchronous networks. Testing has been the traditional approach that engineers use to ensure the correctness of distributed systems. However, it is virtually impossible for testing techniques to cover all edge cases. Bugs then inevitably make it to production, which is something we want to avoid. To address the limits of testing, researchers and practitioners have embraced a powerful approach, that is formal verification. Formal methods are great because they rigorously prove the correctness of the system to categorically eliminate bugs at compile time. In this work, we focus on proving safety properties of distributed protocols. The goal is to show that a safety property P is an invariant. For example, in a consensus protocol, a safety property could be that all nodes reaching a decision agree on the same value. And proving a safety property requires 3 steps. First, we model the system as a state machine. Each global state includes the state of the network and the state of a collection of hosts. Second, we find an inductive invariant I for the system. I is a strengthening of P that is maintained across state transitions. And typically, it is expressed as a conjunct of many smaller invariants. Now, this inductive invariant is the centerpiece to verification. We need it because generally, the safety property P is not inductive. This means that there exist states in the system that satisfy P, but can transition to unsafe states. Hence, we need to find an inductive invariant I that is the strengthening of P. I must be weak enough to encompass all reachable states and be strong enough such that states that satisfy I can only transition to states that also satisfy I. Now finally, after identifying this inductive invariant I, we write an inductive proof to show that I is correct. Namely, that I holds in all initial states, I is maintained across transitions, and I implies the safety property P. Now these last 2 steps are hard. Even simple protocols have a long list of conjuncts in their inductive invariants, and finding each of them manually and proving their inductiveness requires deep expertise. This difficulty is compounded by the way the user has to iterate on both these steps through trial and error. People don't come up with a correct inductive invariant right off the bat. Rather, they make an informed guess as what an inductive invariant is, try to prove it, fail, then go back to make modifications to the invariant. This is a high-effort process and can go on for multiple iterations. And each attempt to prove a futile invariant requires significant time and creativity. The reason is that in general, finding and proving inductive invariants is undecidable. The user must manually supply these invariants and proofs to guide the verifier. In this work, we automate the finding of inductive invariants in this general undecidable setting using our tool called Basilisk. Basilisk helps in 3 ways. First, it finds an inductive invariant for you. As a consequence, this painful iterative loop is also eliminated. Finally, the candidate inductive invariant that Basilisk finds is guaranteed to be inductive. Hence, the user does not need to complete an inductive proof to show that it is correct. Instead, they write a relatively simple, non-inductive proof to show that this automatically generated set of invariants do imply the desired safety property. Of course, by the very nature of undecidability, it is impossible for any tool to achieve this for all protocols. And yet, with the right insights, this problem can be solved for many practical and complex cases. We achieve this by first identifying a class of simple, mechanically derivable invariants that let us track the lineage of a host state throughout an execution. And we call these provenance invariants. We then devise an algorithm to find provenance invariants automatically given a protocol description. And we implement these insights as Basilisk. The rest of this talk has 3 parts. First, I present a class of protocol properties that are currently a bottleneck in automatically finding inductive invariants. For this talk, I focus on inter-host properties, which are properties relating the states of two hosts. Next, our key insight is that these seemingly complex properties can be expressed using simple provenance invariants, which can then be derived automatically. Finally, I introduce Basilisk to leverage these insights. Given a protocol, Basilisk automatically derives an inductive invariant with a few simple hints from the user. Now let's start in part 1. So our prior work, Kondo, introduced an invariant taxonomy that classifies the invariant of distributed protocols into 2 tiers. The lower tier of regular invariants have simple structure, and they concern simple, low-level properties that Kondo could already derive automatically. Then, there's a higher class of protocol invariants that deal with the global relationships between hosts and capture the core logic of the protocol. Kondo did not automate protocol invariants, so deriving them required manual effort. Unfortunately, protocol invariants are also the most difficult to derive, and they require a deep understanding of why the protocol works. In particular, protocol invariants include inter-host properties that express relationships between remote hosts, and also intra-host properties that assert the local properties of hosts. For this talk, we focus on inter-host properties, and I show how we can derive them automatically. As an example of inter-host properties, let's look at this very simple two-phase commit protocol. In this system, nodes agree to abort or commit a transaction depending on the preference of participants. First, the leader collects participant preferences through votes. The leader decides commit if all votes are yes, else it decides abort. It then sends the decision to participants who follow that decision. The safety property we want to prove is, if any participant reaches a commit decision, then everyone's preference must be yes. Now let's try to write an inductive invariant to prove this property. Recall that the inductive invariant I is a conjunct of smaller protocol properties. Many of these are inter-host properties that relate the states of distinct hosts. In two-phase commit, we need 2 such properties. Namely, for every entry in the leader's yes vote set, the corresponding participant's preference must be yes. And if a participant's local decision is commit, then the leader's decision must also be the same. Importantly, while prior work could automate some simple regular invariants, it could not derive these inter-host properties I0 and I1. However, I0 and I1 are conceptually the hardest ones because they deal with how the states of different hosts interact. This understanding can be difficult even for the protocol's designer, let alone a verification engineer working with a pre-existing protocol. In Basilisk, we address this user pain by expressing these inter-host properties using only simple, regular invariants. As such, I0 and I1 are no longer the concern of the user. In fact, users do not have to write any invariants at all. And we generate the entire inductive invariant automatically using a new subclass of regular invariants that we call Provenance Invariants. This brings us to our key insight. Namely, we present a class of mechanically derivable invariants called Provenance Invariants to express both inter-host and intra-host properties. We can then express the entire inductive invariants of distributed protocols using only these automatically derivable invariants. Now, provenance invariants trace the lineage of host state and network messages throughout the system's execution. They're highly automatable and sufficient to express a broad range of inter-host properties. We state provenance invariants using the history of a host. A history is a sequence of states that a host transitions through as it takes steps in the protocol. There is an initial state and a current state. We also consider the current state of the network expressed as a monotonically increasing set of sent messages. Provenance considers how the current state of the system must be a logical consequence of a host taking a particular step at some time in its history. More concretely, suppose we have a receiver host R and a sender S. In the current state, R has local variable x with value 5. This state can be traced back to the protocol step that most recently updated x based on some received message m and implies the existence of m in the network. Message m can in turn be traced to the state of its sender s. This describes a causal chain between R and S that implies inter-host properties. And by transitively chaining such arguments, we can derive relationships between the head and tail hosts of a causal chain of messages. In more detail, there are two flavors of provenance invariants. First is network provenance. It relates a network message to a host step that sent the message. Namely, for a message M, the existence of M in the network implies that its sender must have executed a step that sent the message. The second flavor is called host provenance. It relates a local property Q of a host state to a step that the host must have taken in order for Q to be satisfied. And we call this property the provenance witness. Namely, given that Q is true in some host state and Q is not true in the initial state, then the host must have taken a step where Q went from not true to true. This may be a spontaneous transition that does not receive any messages, or it may receive a message from the network. In this case, the host provenance invariant then also implies the existence of such a message. To see provenance invariance in action, let's return to our two-phase commit example. Recall our safety property that if any participant decides commit, then everyone's preference must be yes. To prove safety, one inter-host property we had to manually write is I1, that if a participant decided commit, then so did the leader. However, we can actually replace I1 with a pair of provenance invariants. First, we write a host provenance invariant HP. It says that if a participant decided commit, then it must have performed a step that received a decide commit message. Next, we write a network provenance invariant NP. It says that for all decide messages in the network, the leader must have executed the step that sent the message. Finally, the conjunction of HP and NP actually implies I1. This means that if we can derive HP and NP automatically, then the user does not need to supply I1 to prove the protocol. And this is exactly what we do in Basilisk. Our second insight is that provenance invariants, such as HP, can be derived automatically using a technique we call atomic sharding. While I defer to our full paper for details, I show you a glimpse of how we apply atomic sharding to derive HP. Atomic sharding associates host variables with steps that update them. First, we identify sets of a host variables that are always updated atomically, meaning that there are no steps that modify some variables in the set, but not others. And we call these sets atomic shards. By definition, the singleton set containing the participant's decision variable is an atomic shard. And next, we associate with each shard a set of steps that modify the shard. For the shard in our example, it is modified by only one step where the participant received the commit decision. And finally, the variables in the shard are used to craft antecedent of HP, while the associated steps form the consequent. So now that we see how provenance invariance and atomic sharding works, I show how Basilisk uses them to find the inductive invariants of distributed protocols. So Basilisk is built as a compiler extension to the Daphne verification language. The user writes a protocol in Daphne and feeds it to Basilisk. Next, Basilisk uses atomic sharding to generate an inductive invariant expressed using provenance invariants. The user then completes the final proof by showing that this inductive invariant implies the desired safety property. This is now a straightforward task, as there is no longer any inductive reasoning. Occasionally, the generated invariant is not strong enough to prove safety, and the user gives some hints for Basilisk to strengthen it. We evaluated Basilisk on 16 distributed protocols, and here's a sample of the results. These graphs show the number of invariants a developer have to manually find when using Condo, which is the prior state of the art. And this effort is reduced to 0 using Basilisk. Next, the bottom graphs count the lines of Daphne proof code that the user writes. With Basilisk, this effort is also reduced. This demonstrates that we didn't simply replace invariant finding with a greater proof burden, and that the user experience is materially improved. Finally, while Basilisk is not theoretically guaranteed to work for all protocols, it works empirically for all 16 protocols in our evaluation, including notoriously complex ones such as multi-Paxos. In summary, manually finding and proving invariance is hard. This is especially so for inter-host properties that were previously beyond the reach of automation. Our insight is a new type of provenance invariants that can be used to express inter-host properties in distributed protocols. We also present the atomic sharding technique to derive provenance invariants automatically. Finally, we develop Basilisk to leverage provenance invariants and its automation. Given a distributed protocol, Basilisk automatically generates an inductive invariant expressed using provenance invariants. The user then completes a simple proof to show that this generated invariant implies the desired safety property. And with that, I'm happy to take questions.